This video presents our work to create self-refining games, where the game physics improve as more users play. Our example game models a water tank. The user can tilt the water left and right. Animation is produced by concatenating short pre-computed clips of video. The user scores points by splashing the water through this area. Our key insight is that, because this is a game, the user does not move the phone randomly, but rather tends to perform certain strategic actions. The challenge is how to use this knowledge to pre-compute only a small subset of the full state space. Mathematically, we model the game as a graph. Each node is a state of the simulation, and the edges are short videos from one state to the next. Simulating multiple control trajectories from a single root state creates a tree. To eliminate dead ends, we can take a leaf edge and find its closest internal edge. We then blend the two simulations in 3D, creating a back edge to an internal state. Some back edges have low error, while others will produce visual artifacts. We remove bad back edges by expanding them and continuing the process. A crucial question is, which back edges should we expand? We compare three strategies. The first, baseline strategy, repeatedly expands the back edge with maximum error. Running this sampling strategy for 4,300 CPU hours using 41 computers yields a large graph with 200,560 states covering 1.8 hours of animation. Each edge is a video clip. Real simulations are shown in blue. Back edge blends are shown in red, and particularly bad blends are shown in bright red. In total, we created 20,056 clips. This game has good settling behavior, but the baseline growth strategy shows considerable artifacts when the user tries to play the game by rocking the phone. In fact, you can see that virtually all of the breaking waves are blended away and disappear. Lowering the viscosity makes the fluid even more animated, and we see even more errors. These errors are apparent in the inset rendering. To address this problem, our state rank algorithm minimizes expected error using a heuristic user model. Suppose the user holds the phone still 80% of the time and rotates the phone 20% of the time. This state rank strategy uses a similar amount of computation, but produces a tree which looks quite different. And we see far fewer artifacts when the user starts actually playing the game. However, when we lower the viscosity, we still see significant artifacts. The artifacts you see are largely caused by our simple heuristic user model. We need to use real user data. To do so, we use crowd-based adaptive sampling. We capture real traces of players playing the game and build a statistical model of their transition probabilities. Using this data, we grow a third graph. The pre-computation time is similar, but this time state rank has concentrated sampling on those parts of the state space which users really explore. This is the key idea of our paper. Using this crowdsourced information virtually eliminates visual artifacts at high viscosity. Even in the more challenging case of low viscosity, bad transitions happen significantly less frequently. Here we show a comparison, highlighting the advantage of our user data. We now show some further examples highlighting the advantages of our system. Because we pre-compute data, we can capture very high-resolution dynamics. This liquid simulation uses 340,000 particles and requires 50 seconds per frame to simulate and 60 seconds to render, but we can play it in real time on this mobile device. We can also vary the control. This game has 4 discrete controls, enabling 360-degree rotation. Thank you.